In the last video, we saw how we could compute an indefinite integral by using an antiderivative. Here, we're going to talk about the definite integral. And this lecture should not make it clear why the definite integral and the indefinite integral share similar terminology and notation. So let's discuss the definite integral. Well, first, remember, the indefinite integral gives a family of antiderivatives. Let's talk about the definite integral. Definition. The definite integral. Let f of x be continuous on closed interval a to b. The definite integral of f of x is denoted integral a at the bottom, b at the top, f of x dx. So the notation here is the same as the notation for the indefinite integral, except we're keeping ourselves on a closed interval from a to b. The definite integral of f of x denoted that is defined by these limits. Integral from a to b of f of x with respect to x is the limit as n goes to infinity of ln, which is the same as the limit as n goes to infinity of rn, where ln and rn are the approximations of the area between f of x and the x-axis using rectangles. These are the approximations we saw weeks ago, and remember, the limit turns those approximations into exact areas. So the definite integral is going to give us something involving the area between a curve and the x-axis on a to b. And remember from, I think it was week 4, might have been week 3, but remember, those limit computations were quite tedious. But they were still doable for some functions. But the definite integral is going to give us an area between a curve and the x-axis. When we discussed that area approximation, we considered only functions above the x-axis, just for convenience, to get used to the approximation. But let's make an observation. I'm going to make this observation about ln. It'll be the same for rn. But for ln, remember that the actual formula for the approximation with n rectangles was a sum. I'm not going to, the indexing won't make this more clear, so I'm just going to say I'll be a little informal in the discussion of this for illustrative purposes. But ln, remember, is the sum of heights of functions times x-axis pieces, and this gave us rectangles. But observe, for this, in that sum, all of our functions that we considered before were above the x-axis on the relevant intervals. But it could be below the x-axis, and the question is, what happens if the function is below the x-axis? So I'll say f of x can be above or below the x-axis. And because of that, if the function is above the x-axis, then f of x times delta x, which will always be positive, but if the function is above the x-axis, then this rectangle will contribute in a positive way to ln. If f of x is above the quantity f of x delta x is positive. And if f of x is below the x-axis, the quantity f of x delta x, well, delta x is always going to be a positive, but f of x is going to be a negative. So that tells us f of x delta x is going to contribute negatively to this approximation, well, to this sum of rectangle areas. So if it's above the x-axis, it contributes in a positive way to the definite integral. If it's below the x-axis, f of x delta x contributes in a negative way to this definite integral. And with this in mind, we get the following remark. Remark. This is really a remark and a theorem and a definition. Let's just start. Remark. Let f of x be continuous on a to b. Let A1, capital A sub 1, be the total area between f of x and the x-axis that lies above the x-axis on a to b. So A1, area between f of x and the x-axis, above the x-axis. A2 is going to be the same thing, but below the x-axis. The total area between f of x and the x-axis that lies below the x-axis on a to b. Then, the integral, the definite integral of f of x from a to b is the area above the x-axis minus the area below the x-axis. And this is negative from what we just discussed with the function in the approximation. If the function goes below the x-axis, then those rectangles are going to contribute negatively to the total approximation, and in the limit, they'll still contribute. In the limit, that'll cause an entire piece of area below the x-axis to contribute negatively to the definite integral. Definition: and the total area between f of x and the x-axis on a to b is a1 plus a2. So total area, we'll treat it as positive. But the definite integral treats what's below the x-axis as negative. So let's look at this function with areas given. So we have a function. First area there is 2. The area below the x-axis is 3. Then that next area is 4 above the x-axis. And we're going to compute 3 definite integrals and then find the total area. So first, from -1 to 3, well, we look at the function on -1 to 3. Well, it's here to here. So the only area between -1 and 3 is above the x-axis, and it has area 2. So in this case, a1 on this interval is 2, and a2 is 0. 2 minus 0 is 2. Next, 3 to 5. The integral from 3 to 5 of f of x with respect to x. Well, on 3 to 5, all we have is this piece below the x-axis. So a1 on 3 to 5 is 0. a2 on 3 to 5 is 3. And 0 minus 3 is -3. So how about on 1 to 7, or sorry, -1 to 7 for part C? Well, -1 to 7 starts here, ends here. Maybe I should put an arrow on that. -1 to 7 starts there and ends there. So what is above the x-axis? Well, there's a 2 and a 4. So they contribute positively. So in particular, on -1 to 7, a1 is 6, 2 plus 4. And what's below the x-axis? Well, there's this 3. So we subtract that. a2 is 3. 6 minus 3 is 3. And part D, the total area between f of x and the x-axis, well, we just treat all of them as positive. So we get a 2 plus a 4 plus a 3, or a 2 plus 3 plus 4, which is a 9. So right here, this function gave us the areas. But we could set up a function so that it gives shapes we can find the areas of, like circles and triangles and rectangles. So let's look at an example like that. So here we have an example function with some triangles, some rectangles, and a semicircle. You could think of that as a trapezoid, but I'm just going to do rectangles and triangles, because area of a trapezoid, I don't know it well, I guess I do know it off the top of my head, but I'd rather just think of rectangles and trapezoids. Rectangles and triangles. So for this function, we're going to compute 3 integrals. The integral from 4 to 6, integral from -4 to 11, and the integral from 9 to 10. But before even doing that, I'm going to just fill in these areas. I'm going to do it by breaking this function into rectangles and triangles. Okay? What's the area of this? So you could do this in two different ways. You could treat what's below the x-axis as a negative here. I'm going to write them all as positives and then interpret them as or with negatives if I need to over there. So first, notice we have a right triangle here. The area of a right triangle is what? Half times the one side. Well, it's half base times height. So it's half of this side times this side. The height is 2. The base is 1. Half of 2 times 1 is 1. So next we have this rectangle here. I'm going to get rid of this y-axis. So it's not there. So the rectangle is the one side times the other. This side is 7. The height is 2. 7 times 2 is 14. So next we have this triangle going through the board division. So it's another right triangle, and the height again is half times base times the other leg. So this side is a 2. This side is a 1. So again, we have a half of 2 times 1, which is 1. Now this next triangle, again, you could treat this as a negative. I'm going to write it as a positive and use a negative over in that if I need to. It's another right triangle. The one side is 1. The other side now is 3. 1 times 3 is 3. Half of 1 times 3 is 3 halves. Next, I need to give you another number. Let's put a 5 there. So that should be down at 5, negative 5. Next, from 6 to 9, we have a rectangle. The one side is 3. The other side is 5. So that gives a 15. With the, if you're going directly by the definite integral computation, you would consider these negatives. But again, I'm going to treat them as negatives using that remark over there with the A1 and the A2. And right here we have a semicircle. Area of a circle is pi r squared. The radius of this circle, notice, is 1. Pi times 1 squared is what? Pi. But we have half of that because it's a semicircle. So there we have half of pi is that area. And now we can find these integrals just by putting the appropriate areas together. 4 to 6. Area above the x-axis is 1. So 4 to 6 is this piece, starting at 4, ending at 6. What's above the x-axis is 1. What's below the x-axis is 3 halves. So we have 1 minus 3 halves, which gives us negative 1 half. How about on 11 or on negative 4 to 11? Well, that's all of these shapes. So what do we get? We get what? 1. What's above the x-axis is 1, and 14, and 1, and pi over 2. What's below the x-axis and gets subtracted is 3 halves, and 15. And what does all this equal? Well, we have pi over 2 minus a half. So the numbers the whole numbers, the non-pi numbers are 16 minus 15, so 1 minus 3 halves gives you negative a half, and pi over 2. You could write that pi minus 1 over 2 if you want. I'm not going to. Next, we have the integral from 9 to 10. Well, where's 10? 10 is right here. 10 is the middle of that semicircle. So the integral from 9 to 10 is just going to be that area, positive above the x-axis. So 9 to 10 fills in this area, which is a quarter of a circle of radius 1, so pi over 4, or you could just take that pi over 2, divide it into either way, you get pi over 4. So we have a nice interpretation of the definite integral with area. That interpretation gives us some convenient definite integral properties, just like we had some convenient properties for the indefinite integral. we have here 5 properties of the definite integral, which is more than our indefinite integral properties, but our definition uses areas, and we have a couple additional consequences we can find just interpreting these as areas. First, integral from a to a of f of x is 0. Now, why is that? Well, remember, the definite integral is defined as the limit. And part of the limit, or the limit of areas of rectangles, of the sum of areas of rectangles. So if we're looking only at a to a, the base for each rectangle is going to be height 0, or is going to be length 0, which causes the area of each rectangle to be 0 in our limit, in our approximation, and because of that, the integral from a to a will be 0. Another less technical way of viewing that is, if you just have a function, and remember, an integral is going to look at an area on an interval, but if we're just looking from a to a, well, the area of that line is 0. Another way of viewing that. Next, integral from a to b is the negative of the integral from b to a. So if you flip the bounds around, it becomes a negative. Now, why is that? Well, it's again, that's because of the delta x portion, or the dx portion. If you flip your interval around and go backwards, those bases of each rectangle are going to be interpreted as a negative for each case. And because of that, the integral, well, because of that, each area's rectangle is the negative of what it was, and because of that, the integral differs by a negative if you flip the bounds around. Next, the next two, C and D, that's a C, that C looked like an E. C and D parallel the definite integral properties, and these two follow from limit properties. The limit of the sum split, the constant in front of the limit came out. These two follow for the same reason. The integral of a sum or a difference of a definite integral is the sum or difference of the definite integrals. And if there's a constant in front, constant times your function, you can pull that constant out of the integral and then compute the integral just from the limit properties. And also part E. This one looks a little different, and I think this is best understood with area interpretation rather than the limit. The integral from a to b of f of x equals integral from a to c plus integral from c to b, where c is between a and b. I guess it could be equal to, where c is between or equal to a or b. Now, what would that look like? Well, to illustrate that, E, observe this. Integral from a to b gives us this area. Integral from a to b gives us that area. There's the other color marker. But integral c is between or equal to a and b, so you can put c between these. And it would give you something like this. There's a, there's c, there's b. Integral from a to c is that area. Integral from c to b is that area. So this fifth one is just a way of saying you could divide area into a couple pieces if you want. So integral from a to b, that area is the same as this area plus that area, and it'll work the same way if you have things above or below the x-axis. You could also see this in the previous example, in the first one we did, when we did the integral from 4 to 6. We technically could have viewed that as the integral from 4 to 5, which was 1, plus the integral from 5 to 6, which was negative 3/2. And that's another way of viewing it. So the definite integral gives us area between the curve and the x-axis, positive or negative, above or below. The indefinite integral gives us a family of antiderivatives. There is no reason to think that that family of antiderivatives is in any way related to this area. But next week, we're going to see the fundamental theorem of calculus, which says, yes, they are related. And they're related in a very nice way.